This video is on the objective determine the critical value or critical values for a hypothesis test for the difference of two population means or two means, but with the population standard deviations unknown, right? So you're going to be working with the student's t distribution here. And when you find those critical values, right, those will help you determine or define a rejection region or rejection regions, if it's a two-tailed test. And I've already done a video on this objective before. This is video number 2, so hopefully you've watched that first one. And let's just get into the question. And if you're unfamiliar with the topic, would like to see more about what they have to say about it, click on More Instruction, look at their videos, their examples, their notes, and hopefully those help you. Alright, so Dylan Reeder, or Ryder, I don't know, Reeder, is a statistics student investigating whether athletes have a better balance than non-athletes for a thesis project. So Dylan randomly selected 32 student athletes and 45 students who do not play any sports to walk along a board that was 16 feet long and 2 inches wide and raised 6 inches off the ground, just to see if they have better balance, right? Dylan recorded the number of times each participant touched the ground. The athletes had a sample mean of 3.7 touches with a sample standard deviation of 2.3. The non-athletes, students, right, had a sample mean of 4.1 touches with a sample standard deviation of 2.5. Alright, so here mu1 is the population mean number of touches for student athletes. Mu2 is the population mean number of touches for students who do not play sports. What type of hypothesis test is this? Is it a right-tailed, left-tailed, or two-tailed? Okay, so let's set up the hypotheses, right? So remember, every hypothesis test starts with some sort of belief or something, some statement being investigated or some claim, right? Now, what this person is investigating is in the first sentence. It says he's investigating whether athletes have better balance than non-athletes. So that means remember what these mu1 and mu2 mean? The number of times they touch the ground when doing this balance test. Now, if the athletes have better balance, if he's testing whether or not they have better balance than non-athletes, then the number of times they touch the ground on average when doing this balance test would be less than the number of times the athlete students did. Right? Because if they're able to stay on the beam longer and not touch the ground as much, that means they have better balance. So hopefully that makes sense why I have mu1 less than mu2 here as the claim. Now, an alternate way of stating this is that mu1 minus mu2, or the difference between these means, is less than 0. So again, I think that might be the hardest part here, is reading the word better and interpreting it as less than, because it was number of times they touched the ground. Alright, once a claim is established, right, then you set up your hypotheses. You have your null hypothesis, your alternative hypothesis. This claim, again, does not involve equals at all. So that's going to be represented by the alternative hypothesis. mu1 minus mu2 is less than 0. Alright, then the null hypothesis should be the opposite statement of the alternative. The opposite of is less than is greater than or equal to. Now, that's a perfectly valid null hypothesis. But when you actually go through and perform the steps of the test after this, what you're going to be assuming is the equality part. We would assume that these mean values are equal, or that their difference is equal to 0. All right, and then the way the alternative hypothesis looks tells us what kind of a test this is. Is it a left-tailed test, a right-tailed test, or a two-tailed test? Well, we have the parameter less than some value, so this is a left-tailed test. Alright, so when I go to find critical values later, there's only going to be one of them. Should be left of the mean. And then the area to the left of that critical value should be the value of the significance level alpha. There's only the one left tail rejection region. But we're not given any of that yet. We're just asked to determine in the beginning what kind of a test it is. And it's a left-tailed test for the, now again, for the right reasons though. This would be a right-tailed test if my alternative hypothesis looked like this. It's this last statement, right? It's a left-tailed test because I have mu1, this mu1 minus mu2 is less than 0. Okay, wonderful. Read your answer explanations. And then there's a second part to it where you're actually then finding the critical values. Now, Dillon used the alternative hypothesis, HA, the one we just set up, with alpha equal to 1%, right? So a significance level of 1% and 75 degrees of freedom. So Dillon here, it looks like, 75 is the, you add up the sample sizes in -2. Right, 32 plus 45 minus 2. So it looks like Dillon assumed that the population variances were equal, right? This is one of those pooled scenarios. Hopefully you recall that from a previous assignment. And in those pooled scenarios, the number of degrees of freedom for our student's t-distribution is the sum of the sample sizes minus 2. Alright, so looking at a student's t-distribution with 75 degrees of freedom, and then we're asked, okay, where would be the rejection region, right? What is the critical value for this hypothesis test? Right. And notice, since we said only left-tailed test, notice how they're only giving us one option here. There should only be one critical value. Alright, so I'll go draw a picture of this, what we're looking at. So again, after hypotheses are set up, usually a significance level is identified. That was 1%, right? 0.01 here. And that'll be the area of the rejection region. And our sample differences, x1 bars minus x2 bars, the distribution of these sample differences in this scenario is a student's t-distribution with 75 degrees of freedom. I'll draw that. All right, so here's a number line representing possible t-scores. It's a symmetrical bell-shaped curve, right? Similar to a normal, but not exactly. Underneath the peak is a t-score of 0, and we have a left-tailed test, right? So there's only one rejection region, and it's to the left of the center. So here's our rejection region. And the area of the rejection region is alpha, right, 0.01. So what we're looking for is what's the t-score that has 1% above it, but then the opposite of that. Right? So we're looking for minus t.01. That can be gotten from our calculator with the inverse t function, or they give us a table here. So you see there's 75 degrees of freedom. So I'm looking at this row. And this, we're looking for the t-score that has 1% above it, but then the opposite of that, so it has 1% below it, right, using the symmetry of the curve. So I go to 0.01 here. So a t-score of 2.377 would have 1% above it in a t-distribution with 75 degrees of freedom. So, the t-score over here on the right, 2.377. So that this score with 1% to the left is negative 2.377, and that would be our critical value, negative 2.377. Right. And then we'd have a test statistic and determine, does that test statistic fall in this region or not, and then would we reject the null hypothesis or not, and then you make a conclusion. But all we're asked for here is the critical value, which again, be careful, this is negative 2.377. Positive 2.377 wouldn't be good. That would be for a right-tailed test. Yeah, wonderful. All right. Yeah, read through your answer explanations. Hopefully watching me do this, looking at the more instruction, reading the answer explanations, hopefully all this stuff helps you when you're working on these assignments on your own. And thank you very much for watching.